Okay, so, the Big Bang is a theory. It's supported by lots of circumstantial evidence. But of course, and that's enough to give us high probability, that we use circumstantial evidence to, convict people of crimes, etc. And, almost always it works. So there's a high probability that there was the Big Bang, very high. We can't see it, of course. But then you can say, we believe strongly in elementary particles. The quark, for example, is the fundamental constituent of the proton. No one has ever seen a quark, but we have very strong evidence, circumstantially, that it does exist. We can see it indirectly, as it were. Okay, so let me I'm going to start off by telling you about some of the characters in this amazing story about the beginning of the universe. And maybe the person who deserves most credit for our understanding was Georges Lemaitre, who was both a priest and a scientist. And he famously said, "It appeared to me that there were two paths to the truth, and I decided to follow both of them." Meaning that for him, physics took you back to the beginning, and what happened before then was, a question for him of faith, for others of superstring theory, which I'll come to in the end of my talk. And here we have Pius XII, who launched one of the major encyclicals about belief versus science and being compatible with each other. And Lemaitre eventually became an advisor to the Pope, etc., and had a glorious career afterwards when he did less science. But at the beginning, in his 20s, 30s, he was a very active cosmologist. And here is another quote from him, one of his books. The first instant at the bottom of space-time, we refer to space, our three dimensions, and time as one continuum, as Einstein taught us. The now which has no yesterday, because yesterday there was no space. So for him, things did begin at time zero. And there's another beautiful quote, one of my favorites from him. So he studied the way structure developed in the Big Bang, which he was essentially a co-founder of. The evolution of the world can be compared to a display of fireworks that has just ended. Some few red wisps, ashes and smoke, standing on a cooled cinder, that's the Earth, our galaxy. We see the slow fading of the suns, and we try to recall the vanished brilliance of the origin of the world. And that's what astronomers do. So here is the gang, as it were, that have made it such a high probability that there was a Big Bang through many contributions, both to theory and observation. So, for example, we have Edwin Hubble, the co-founder of the discovery of the expansion of the galaxies. Lemaitre, the other person who was a co-founder, and Alexander Friedmann also, who did not really think much about the galaxies, but was more of a mathematician, but also played a key role in the story, and Einstein and Lemaitre discussing their views. Eddington, the first person who brought Lemaitre's rather obscure work, because it was published in French, to the attention of the much wider world in 1931 or so. Another key, a Dutchman, proponent of the theory with Einstein. George Gamow, who was the first person to really develop the idea that the Big Bang was very hot at the beginning and therefore was a great furnace where many interesting things could have happened. Fred Hoyle, who hated the Big Bang, and because it seemed to him such an absurd concept. And then the two scientists who made a fundamental contribution by discovering the fossil radiation in the beginning of the universe. Maybe our most important evidence for the Big Bang. Okay, so Einstein proposed in 1916 an amazing theory. He had a new theory that supplanted that of Isaac Newton. He generalized Newton's theory, the theory of gravitation. And for him, gravitation was property of space, matter curves space, and the paths of objects around due to gravity were basically paths in space. It was a wonderful idea, but as far as and he applied his theory to the universe. He wanted to do cosmology, but for him, he had no notion that there could have been anything other than a static universe. There was no reason to believe that at the time, in 1916. So he had a static universe, and then along came the two scientists that upset his view of the world. Alexander Friedmann, a Russian mathematician, meteorologist, and Mettrie, who was an astronomer cosmologist, basically. And so this comes from Metrie's notebook in 1927, just a decade after the Einstein's theory was announced. And just a few years after, it was also verified by the famous bending of light around the sun. And so here are various models of the expansion of the universe, which Mettrie discovered. And so here is one that expands and eventually collapses to what we call a big crunch. Here is one that expands more and more slowly but goes on forever and ever. And here are some that accelerate eventually and start moving faster and faster. So that was Metrie's contribution. But what he also did, which his predecessor, Friedmann, did not do, was he had access by visiting Pasadena, eventually the observatories there. He had access to the data, and he applied his model of the expansion to the data. And so he did much what Hubble had done a little bit later, and essentially discovered the expansion of the universe. So let's just look at that. So when he confronted Einstein with these ideas that the universe could be expanding based on data and Metrie's models, which Einstein at that point finally was beginning to believe might be possible after a long debate with Metrie's predecessor, Friedmann. Einstein, your calculations are correct, but your physics is atrocious. This is too much, suggesting a creation, the Big Bang. So Einstein didn't like it at all. Mettrie, the hypothesis he called his class of models for the atom, it's the antithesis of a supernatural creation. So for him, it had nothing to do with any mysticism or anything. It was just simply a consequence of physics. And so Einstein converted. And so here is a classic photograph taken, I guess, posed for the newspapers, because in the light he couldn't have been seeing very much. But Einstein and Hubble at Mount Wilson in 1931, and Edwin Hubble, who had discovered and published a couple of years before his evidence for the expansion of the galaxies, showing to Einstein the data, presumably some view of something, and Hubble had demonstrated the universe was not static. And because it was not static, that had immense consequences for its interpretation, as we'll see in a second. And so Einstein changed his mind. And on a lecture tour with Mettrie in California a couple of years later, he said, "This is the most beautiful and satisfactory explanation of creation I have ever listened to." So things did change. That was a very intense period, those few years at the end of the 1920s, early 1930s, when our beliefs were really having a radical change in how the universe began. So that's where things were for quite a long time. And then in 1990, in 1964, I should say, I'll come to that in a second, the relic radiation from the Big Bang was discovered by Arno Penzias and Robert Wilson using a telescope that had been abandoned, used for the early satellite communications at Bell Labs. They gave it to the scientists who worked with them, and these two gentlemen studied essentially the Milky Way, but they found this unaccounted for whisper from the sky, which later turned out to be the fossil radiation from the Big Bang, pure black body radiation, as later experiments demonstrated. They discovered this. And so this essentially proved the Big Bang began as a perfect furnace. And the early data were maybe not totally convincing, but then along in 1990 came a satellite experiment which measured the spectrum of the radiation, the intensity at different frequencies, and proved to incredible accuracy that was exactly that of a perfect furnace. The universe cooled down, but the radiation was left behind, greatly cooled down to a temperature of effectively a few degrees above absolute zero. The 3 degrees, we call it a 3-degree cosmic microwave background because it emits mostly microwaves, but its spectral shape proved that it came from an incredibly hot, perfect furnace in the first seconds, the first minutes maybe of the universe. It was hot enough to produce this highly thermalized radiation, which you could only see in a perfect furnace. So there we were, and then the next big step was this, that for many years people just studied this radiation, but they realized the radiation had to have ripples in it, because otherwise one would never have made the galaxies, the stars, the planets. We would never have been here. So one had to see some deviations from this beautiful symmetry. And it really took convincing evidence from an early satellite experiment. They launched a microwave telescope, and these gentlemen, John Mather measured the spectrum I just showed you, and George Smoot led the experiment that measured these fluctuations. And the ones on the left were announced in 1992 to great acclaim. And then over the years since then, the 2 decades since then, we've now launched much more refined satellites. This is the latest one over here, the Planck satellite, and that produced a very detailed map with, you can see slightly colder spots, slightly warmer spots, but these spots are tiny differences in temperature, which mean there were tiny density variations, which are the seeds from all the structure we have in the universe. So that was an immense accomplishment, and at the time, 1992, it got incredible publicity. So this is one example from one of our almost existing newspapers still, how the universe began. Incredibly exciting at the time, and it still is for many of the scientists, even because it is the best testament we have to the very, very early minutes of the universe. Okay, so this led to a very big mystery in the decades that followed that discovery. And we call this the mystery of dark energy. So going back to Einstein, he had to make the universe static, and he realized gravity would force it to collapse. Things collapse under gravity. So he invented a constant of nature, and he called it the cosmological constant, which basically had the opposite sign to gravity and acted like anti-gravity, okay, that for him. And so he inserted this into his equations. His equations said essentially that the curvature of space is where, this might be where the sun is. Space, symbolically, you can see Einstein's picture reflecting the curvature of space here, but space symbolically is being slightly curved, and this will be where mass is. Okay, so this is distortions from Euclidean geometry reflect mass, and they're equivalent to each other in Einstein's new theory. And so he has then in this system of his, and I apologize for the algebra, but this is the only slide I show with any tenses on at least. So he added this mysterious constant denoted by the Greek letter lambda, which acted against gravity. And over here you have all the source of energy and mass in the universe. And these are Einstein's famous equations of general relativity. But then they discovered the expansion of the universe. And Einstein said, let's get rid of this arbitrary constant. Let's set it equal to zero. Then we suddenly have the expansion of the universe acting against gravity, and things are fine. It all works out. But Mettrie did not agree with that. So he said, once you've opened Pandora's box and got something like this, it's physics, it's got to be there. Let's put it on the other side of the equations along with the matter in the universe. And suddenly we have a form of matter that can act like anti-gravity. Okay, there's lambda term. And because it's invisible, we now call this dark energy. Okay, it's a form of anti-gravity, and I want to try to explain to you how it works. So this is just from Mettrie's paper in 1933, actually, talking about this is negative pressure I've highlighted there, because pressure in Einstein's theory is a source of gravity, like energy is. But if you make the pressure negative, I'll explain what it is in a second, then it can act like anti-gravity. And this was a prediction of the quantum theory, just beginning in those days in 1933. And Mettrie had the amazing foresight to interpret this dark energy as being a quantum effect. And that's how we regard it today. Okay. So before I talk more about that, just to fast forward you to the vindication of Lemettre's ideas. So now we have the modern version of what we call the Hubble diagram, the expansion of the universe. And these are galaxies with their redshifts plotted, their distances plotted, at many, many different distances from us, going further and further away. And so this means basically nearby, far away. And you can see tiny deviations from a straight line, which means they're going faster than they should be, which means the universe is accelerating. Okay, so we're gradually accelerating. We're seeing that as we look back in time. And it's interesting to see what Lemaitre did in 1927. So this is taken again from his notebook. These are the data points he had, and he plotted them, and you can see the velocity, which is one of these plot axes, is increasing with distance. That's the expansion of the universe. And the amazing thing is that 2 years later, Edwin Hubble had the same data basically, because Hubble in fact got some of that data himself. That was his brilliant contribution, but he obviously had shared some of it with Lemaitre, and you can see it's a very similar result. But we call this the Hubble Law, nevertheless, and maybe we should revise that name. But this was the by 1931, the community was convinced the universe was expanding, and so this is why it's such an amazing proof of acceleration, because this object over here is a supernova. Okay. And we know exactly how bright it should be based on observing many nearby ones. It's an exploding star. And they're like basically measuring sticks. We know how bright they are. So if you see them far away, that tells you how far away that galaxy is. And we find that we look at the distant galaxies, they simply are too faint. By a significant amount, maybe 10 or 20% for galaxies far away, these supernovae. Okay, therefore the galaxies are further away than we think they are, because we measure their speed at a certain speed, they're further away, and therefore that is evidence for the acceleration. For dark matter being basically, which is what gives you the gravity basically, all the matter, everything dark and whatever, but mostly it's dark, being opposed by this weird dark energy force. So how on earth does this strange stuff work? Or the Nobel Prize was given to discoveries of this. They discovered this in 1998, this acceleration, but let me move on. Okay, so let me try to summarize. They discovered acceleration. It's like anti-gravity. It's a new dark force. But there was a surprise. It's incredibly small force. It has an effect because it acts over very large distances. But if you were to measure it nearby, it'd be really, really small. The modern interpretation, which was Lemaitre's as well, says this is a property of nothing. It's the vacuum. And I want to try to explain this amazing concept to you. Okay, so Einstein tells us that pressure, it's a form of energy, and energy is a form of mass, and that basically is attractive, right? But the vacuum is totally different. And so the vacuum has its own energy and pressure due to tiny, tiny fluctuations that come and go on a time scale so small you can never measure anything. It all looks empty. But the theory, the quantum theory, basically what we call Heisenberg's uncertainty principle, which you may have heard of, tells us that stuff is happening in the vacuum. It's just that we can't measure it. But all this happening, effectively this activity in the vacuum does manifest itself as a pressure. Okay, so why on earth is this pressure negative? So ordinarily, if I take a gas, I compress it, okay, the pressure gets up, it goes higher, right? But if I do the same thing to the vacuum, the opposite happens, because the more the vacuum is, the more I depressurize it, the more, essentially, the more fluctuations I have, and therefore the more pressure I have, right? It's a weird property that comes from the quantum theory. So this piston analogy shows you what happens. Imagine this is the vacuum as predicted by Heisenberg's principle, which says that, you can never measure something precisely, because if you try to say where it is, you never know when it's there. And if you So position and time are totally mixed up together. And so that manifests itself as a pressure. Things come and go. You can't measure anything, but you can in principle feel the pressure of uncertainty, basically. And of course, when you expand the piston, you get more volume and therefore more pressure. The opposite of ordinary pressure. That's negative pressure, and that's why it's anti-gravity. So that's the amazing quantum effects happen on the largest scale in the universe. It's an incredible concept, but it's our best understanding to date of why the universe is accelerating. But it's left us with an amazing puzzle, okay? Because now we do the budget of everything in the universe, we find that most of the energy, the density of energy throughout the universe is in this dark form, this weird dark form, pretty much uniform, but exerting this anti-gravity effect. And the stuff that exerts the gravity effect, whether the atoms, the stuff that we're made of, also this mysterious stuff called dark matter, which is even more predominant. We think it's some weird particle, whatever, but it's certainly there, we think. And we observe a certain density of it, a very small amount. But the theory of the beginning of the universe that we have at the moment says it should be much larger. And the error in this calculation is enormous. So it's, many, many trillions. And it's been called the worst prediction in all of physics. So something is wrong. So this is a wonderful discovery, but it means we better get back to basics and try to understand what's going on. So that's sort of what we're busily trying to do at the moment. Okay, and so the solution to this, the possible solution, has come from a whole new revolution in physics called string theory. And I try to say in, as easily as I can what string theory is. So first of all, it's something in higher dimensions. So, just like Buck Rogers and whatever, how many dimensions he lived in. But we now need 6 extra space dimensions, okay? So these are, when I concede this to elementary particles in this weird space, then I can have a wonderful explanation of all the particles we know. Now, I should say the size of these extra dimensions is so tiny that we don't measure them. They're all curled up today. But at the beginning of the universe, that wasn't true. Everything was sort of equal then, and that's where it could have had an immense effect on the beginning of the universe. So another really fascinating property of these extra dimensions is that they give you shapes of the space that they fill in this 6-dimensional space, 6 extra dimensional space, 9 space dimensions, or we have 3, so 3 plus 6 is 9. So they give you different shapes, and they give you a whole lot of different shapes. Every shape corresponds to a separate universe. And we call this ensemble of universes the multiverse. Okay, and in each universe, there's a different set of constants of nature. And one of those is the dark energy, right? So in each of these universes, each one is, now, in some of them, dark energy will be so large, the universe will accelerate so much that any planets, they'll be ripped apart, right? Because of their acceleration, they couldn't even exist, okay? In others, they may be so compact, the universe will collapse, and there wouldn't be time to make any stars at all. So most of these are useless, but the fact that there are so many means that there might be one that is just right? That has just the right low amount of dark energy that it could survive for a long time, and the stars would have time to form, etc. And so that is what our best explanation at the moment for this incredible paradox. And I'd like to say a little more about that now. So let's get back to strings first of all. So here is a sketch of what a string is. So normally, you may remember from early physics, we think of Niels Bohr's model of the atom, a nice sort of spherical nucleus with electrons in orbit around it, and you get radiation because the electron jumps from one orbit to another, right? It either absorbs by, if it goes one way, or emits in the other as it changes energy. But now, and there's a way of regarding this. You have 2 particles coming together here and produce scattering or annihilating or whatever, giving you other particles. But now in string theory, we replace the notion of point-like particles by one-dimensional entities, right? And we call them strings. So suddenly we have this, and they're rapidly oscillating, energetic things, these strings. And they turn out to give you a wonderful explanation for all of the particles in the so-called standard model of physics. And so it's probably one of the best models we have. And you may ask, how on earth do you test this? Well, if there really were lots of these strings in nature, and they all who are in this high dimensional space are when they do leave behind some relics. One relic are lots of strings in three-dimensional space, strings of very high energy from the very, very early universe, and they would leave an impact on the microwave background. So we haven't seen this yet. One of the more elegant predictions of this theory is that when you look with incredibly high detail at the microwave background, you might someday see these sharp edges and little cracks, as it were, in the radiation, the fossil radiation, and that would be a prediction of this network of strings sketched over here, which would be a relic from the string theory that was there very, very early on. Okay, so that's an aside, really. Let me now show you one of these shapes. Okay, so this is a typical shape, as viewed by an artist, of course, and the size of this is incredibly small, so we don't see these now. They're highly curled up now, but in the beginning, when the Big Bang was just getting underway, they would have been the dominant thing, really. And because there are so many possible shapes, we believe that each one of them would lead itself into being a universe. And the whole ensemble of all these shapes is called the multiverse, each with many universes. So this sounds like a beautiful piece of speculation. And here is an artist's sketch of all these different universes, only a small fraction of them, of course. But what I'd like to tell you is there is a way now to try to make something more of this. So first of all, the reason that we have some confidence, at least in the notion of string theory, I mean, this is an amazing prediction, but string theory per se, which leads to this possibility, does explain our standard model of all the particles. So this is a sketch of all the particles that we know about, and the newest one is called the Higgs boson, discovered just 5 or 6 years ago, and that was the missing link in the whole theory that was predicted. We found it, and so these particles then fit beautifully into string theory, and it turns out that, of all these many, many universes, most of them have different values of these particles, the wrong masses, whatever, but one in 1,000 probably is okay for our standard model. So that's pretty good, okay? This is what we call fine-tuning. We're taking a subset of all possibilities, but that's fine. The trouble is, that, of course, that for dark energy, it's a whole different ballgame, right? Because now we suddenly need to fine-tune to do something special out of all these vast number of options. I gave you many, many trillions. That corresponds to 0.00 followed by 120 zeros, 1, etc. But because we have so many different shapes, so many different universes arising from what is actually called superstring theory, which is a slightly quantum version of string theory, that maybe we're okay. We could be happily end up in the right one and explain this weird coincidence that we have such low dark energy compared to what is the natural value, because those universes simply wouldn't be able to make stars and planets. We would not be in any one of them to do our observations. Therefore, it's in some sense it's we call this an anthropic selection effect, which is. It's hard to dismiss that. Of course, it's not actually in the physics of cosmology, but it's an addition. But it's persuasive for many people. So here, for example, is one of my colleagues who writes, "We live in one tiny pocket where the value of the cosmic constant is consistent with our kind of life." Okay, and we can and the counter argument is that the multiverse theory that is accounted for by all these many, many universes, each one is a universe, right? Can't make any predictions because it can explain anything at all. I mean, in one of these, for all we know, there could be fairies living or whatever. I mean, anything seems to be possible, right? Because you can possibly violate the known laws of physics. But we live in one that's just right. So there are skeptics of this viewpoint that it's something that is not testable in any simple way. So that's one of the issues that we have to wrestle with, and I'll come back to that too. Now back to anthropic. So it really is the Goldilocks idea. So there's just one bowl of porridge, unfortunately belonging to the little bear, that's just right, okay? And that just the right temperature, etc. So there's just one universe out there of all these vast numbers of universes in the multiverse that did have time enough and was cool enough and didn't have too much acceleration blasting things apart that life could form on planets in that universe. So that's and all the others are, you could think are sterile. And so in some sense, our presence selects the universe we're in. It's a strong idea, and it's hard to say it's wrong or not. But what you can say is that this is not necessarily physics. Okay, this is adding something to physics, which is why it's a controversial idea. Because ideally, you'd like the ultimate physics theory not to need to appeal to some aspect like this, but to explain everything naturally, including life. Okay, so that finally we have now developed an explanation for the multiverse. So I said there could be all these many universes. So now we have a theory in cosmology, first developed in the 1980s, that says that it's inevitable, okay, this theory. So let me try to explain what that is. So first of all, it's called the inflation theory, and it says the universe went through an incredibly rapid expansion in this quantum era and became enormous, okay? So it starts off from the quantum scale, basically, but then certain effects come in. It's a bit like a phase transition when, water turns to steam or ice to water, that releases a certain amount of latent energy. It's somewhat similar in that sense. A huge amount of energy does get released when you change the nature of the particles there. And this is thought to suddenly give you an enormous injection of energy which can expand the universe dramatically. And suddenly you can end up with a huge universe, corresponding to the one that we see perhaps. And also, because it expands so much, it's like a wrinkled balloon. You blow that up, it becomes very flat. And space is very, very close to being Euclidean. Three angles of a triangle up to 180 degrees, measured to very high precision now from the microwave background experiments, actually. And we have to explain that too. And so this expanding wrinkled balloon idea is a beautiful explanation of that. And these wrinkles, they don't all, some do in fact survive, some of the real knots in space-time, and they can be the seeds of the galaxies. So this theory can give you nearly anything, okay? It's been the only real revolution in cosmology since the days of Einstein and Mettrie, etc., etc. This is the one new thing that has become, I would say, reasonably convincing, but there's still loopholes in this theory and not everyone accepts it. And those were the two founders. So let me just show you the two options we have now. Before that invented this theory, we thought the universe, more or less, what you see is more or less all you have. We can see most of the expansion. There's no reason to think it should be any larger. But there is now a definite prediction from inflation, which is a bit mind-boggling, that we live in just a tiny part of this huge universe. And so who knows what is out there? We like to think from simple arguments that there shouldn't be any gross changes in a few billion years as we expand, double our size maybe, out here from what we see already. There could be, for all we know, might be very unlikely, but in any case, we're just part of some almost infinite landscape of galaxies and so forth that we can never communicate with, because this red circle is what we call our horizon, which is as far as you can see, as far as light has gone since the beginning of the universe, since the Big Bang. In other words, about 14 billion years old, so 14 billion light years is its radius, roughly. And so that's it. We can't see any further. As time goes on, that horizon will expand. Maybe we'll see more and find out more. But that will be our distant, descendants if they're around in who knows how many billions of years. But those are long time scales, and it's hard to, So anyway, so there we are for inflation. And so here is the amazing thing that inflation can also do. It can generate many, many big bangs. So people argue a little bit about how natural this is, but there's a whole class of inflation theories that does this. And basically inflation can occur not just once in the past, but anywhere at any time with some low probability. But if the universe is large enough, that's going to happen. And what's more, if a space inflates, it gets to be very, very big too. So you have all these possible big bangs, and the big, which inflation theory says should happen at any time. We'll have to wait a long while for the next one to occur in our vicinity, no doubt, but somewhere else it could be happening. And in any one of these that's big enough, then the idea is that could be the multiverse, part of the multiverse, the one in which we live, if in that particular patch of the metaverse, the dark energy, etc., and all the other constants work out. And given so many possibilities, the chances are that there should be such a nice confluence of possibilities. So that's our hope. And again, so this is beyond even inflation, right? So here we have the inflation picture I showed you, but this is one patch, just of one, one Big Bang, and that Big Bang, there may have been others spontaneously inflating all over the place, and there could be vast numbers of them. So in some sense, this sets the framework for the multiverse, and it's the multiverse that we can now appeal to try to handle our issues with the dark energy, this incredible paradox in physics. We can try to understand that better. Okay, so that worked very, very, very well up till quite recently. And quite recently there's been, the trouble with cosmology and the beginning of the universe, the so-called quantum cosmology, it's highly uncertain. We don't actually have a theory that unites the quantum theory and gravity. We speculate about theories. You have good guesses as to what they are. And the good guesses have led us to all these shapes and universes in the multiverse. That was one guess. But now, in the past year or two, people, my colleagues, have made other guesses, which they think are better guesses. And they are finding that they've entered what has been called the swampland. And so the swampland is a prediction of the multiverse that's very, very bad for explaining this paradox, because it says that all of these wonderful universes, I said they could have different amounts of dark energy in. It says that in those universes, the dark energy won't be the accelerating type of dark energy. It'll be dark energy with the opposite sign. It'll be compressing. It won't be the anti-gravity. It'll add to gravity. That is the prediction from now. What we are told, my colleagues say, is their latest guess as to what quantum cosmology might be. Okay, so this is bad. It means that you're going to have a big crunch in the future, and that's going to perhaps be sooner than you'd like in most of these universes. And in fact, because it happened so soon, the odds of finding just the right one, solving the Goldilocks problem, have now gotten much, much less. Okay, and so people are in the field are scrambling to find solutions to this problem. Something will emerge, but right now we don't anymore have very, very strong reasons for believing in the multiverse, which might be a good thing, actually, I think, because first of all, it's totally untestable if there is a multiverse. And, you could say maybe, in fact, untestable doesn't really matter if you have a good enough theory, but now the best theory we have is becoming pessimistic. And so what do you do? Well, you could say, maybe this is the most popular counter to all of this, is that the reason this dark energy is so small, this amazing paradox of physics, is just because it is small, because it always was small. What it is, it's just the way it was. And it's just basically another constant of nature. The universe began by concepts that we don't fully understand in our beginning of the universe theory, but constants were assigned. We don't necessarily have to explain all the possible values of these constants. Maybe there was, just as particles of certain masses, why should we, stay up late at night worrying about why a particle, the proton, is a certain mass? And we have an answer to that when it's made of the quarks, but why does a quark have a certain mass, etc.? And it's just, it's just the way it was. Or that's one approach, which I would say is the simplest one. We're just waiting for the right theory, which some have called the theory of everything, which will explain, that was one of Stephen Hawking's favorite words, which will explain all of this. And that may take a long time to develop. We've only been doing cosmology now, for a century or so. Think of what could happen if you now come back in 1,000 years. I'm sure we'll still have our scientists, and Brexit will be over by then, whatever. So right, okay. So we have all this time, and I'm sure theory is going to develop more. Okay. So let me sort of conclude by trying to give you now our picture of the universe, and I'll tell you what my speculation is at the end about what the best options are. And so here today, 13.8 billion years or so after the Big Bang, as we look back through our biggest telescopes, we make them, the bigger they are, the further back you can see. We can see we're already studying when the first galaxies were forming, there were stars were forming 200 million years after the Big Bang. Before the first stars, there was the Dark Ages. Very hard to probe, but fortunately gas clouds must have been there that were assembling to make the first galaxies, and we can study those in radio waves. We may have to go a long way to the moon to do that, but to get away from the Earth's radio interference, but that's a whole other story. And then we have the fossil radiation of the Big Bang, which acts like a fog in the sky, but was produced basically 380,000 years after the Big Bang. And we infer what happened before then, and before then in the first minutes, this was the great contribution of George Gamow and his collaborators, that's when many of the elements were created, the lighter elements were created in the incredible hot and dense parts of the early universe, and that fits the observations beautifully. And then before then, we worry a lot about the formation of all the ordinary matter. There are theories that think we fully understand that. And then you go back to a time when we're beginning to lack a theory, and we've written the words there, quantum fluctuations, and that basically means a big question mark. But those are thought to be the origin of everything, basically, that came from the uncertain physics of this early epoch, and which led to this dramatic increase in size of the universe over here called inflation. So, okay, so let me tell you what I would like to be, and some of my colleagues probably will think the same way, but not all, is the best solution for all of this. Okay, so Fred Hoyle, who invented the word the Big Bang, in a sarcastic series of broadcasts on the BBC in 1951. It's an irrational process and can't be described in scientific terms, he said. We're beginning to disagree with that now. We're developing theories that can address that. But we do need a better notion of the beginning of the universe, that's for sure. And that, I think, is lacking now. So here is what I think the ideal notion would be. Okay, it's something which has been labeled the Big Bounce. Okay, so the idea is that if you follow the universe back in time, you come to a point where it was the Big Bang, if you like, but before then, there was a much, much larger universe that was slowly contracting. And this could have been contracting forever, way in the distant past, and then it reached a point of no return, as it were, and there was and then began to expand rapidly. So it's like a bouncing ball, right? So when you bounce a ball on the floor, the actual physics of the contact of the ball with the surface of the floor that makes it bounce is actually more subtle than you might think. It's beyond Newtonian physics to understand the physics of the interaction of those molecules. So it does involve, we could understand it now, of course, but in some sense also the reason the universe will start expanding again, we don't know it, but it got to some incredibly dense state where all these new theories of quantum theory and cosmology must apply. The trouble is that we don't have such a theory, and we're waiting for it, but I'm optimistic that one day we'll have a much better understanding of the beginning of this so-called singularity in our understanding of cosmology, which is what we're at now. We're going to have to make all these speculations about quantum cosmology and the multiverse, and we will have a well-defined beginning state which could have lasted forever from some indefinitely large region which very, very slowly collapsed. And then, so the whole problem of what happened before the Big Bang would then be resolved by this rather, I think, elegant solution, but we don't yet have the means of proving this. But I suspect that will come someday. So I'm optimistic for theory, at least. So thank you.